This video series is dedicated to a very special person. Probably the most important person when it comes to cold fusion research. Dr. Edmond Storms, Los Alamos Labs, 1989, circa 2012 to present. Research, applied physicist, doctrine in cold fusion. Dr. Edmond Storms, in my professional opinion, is the only physicist who has properly disseminated and clarified a theory. I'm an applied physicist. I very rarely do theory. However, I quantify and clarify theoretical and applied physicist work all the time. I do that professionally. I'm very comfortable for what I'm going to do. However, I'm going to do something uncomfortable at the end of this video. So please bear with me, because as an applied physicist, I clarify my work in little baby steps. I let the findings teach me. Then I go to the next step. Once I get to a certain amount of steps that I can repeat, then I do a change. At this point in time, I'm about to do a change. So I took my lab samples to the lab. These are my Summa bottles for gas pressure, for my 2 atmospheres, my wet and my dry. Both of them are hot fusion. I am a hot fusion expert, professional. That means I've been paid. However, Dr. Edmond Storms was gracious enough to open up his home to a good friend of mine, Captain Bay, on our way back from Los Alamos Labs, where I purchased an entire pulsed plasma physics lab that was in operation from the 60s until the late 90s. And the doctrine that ran the lab, these guys were pulsing millions of volts into the body of an airplane and taking slow motion photography so they could study lightning bolts. That must have been a lot of fun. Okay? On our way home, Edmond Storms opened up his door to his private lab. The videos are in a very special page on my website honoring the life work of Dr. Edmond Storms. Today, I'm going to do something very important. I'm going to clarify and quantify and validate Dr. Edmond Storms. Here's the risk. He's already very, very upset at me, because when I went to his lab, I told him I could run that reactor in a moment, because I already had the tiger by the tail, because I already unleashed the tiger. As I say, I'm a lion in this arena. I'm about to have a big piece of meat right now, which is okay because I eat meat. So I'm going to introduce you to the lovely fusion reactor. And so This is a wet, hot, steamy, lovely fusion reactor. You've seen the basic first fire, okay? That wasn't the first time. I've been doing this since 2006. I met Edmond Storms in 2014. I was very quiet as I possibly could be during our interview because I just wanted to listen to what went wrong and maybe I could help. Because the first words when I walked into the gentleman's home were, if you're bothering with fusion, there's no money in it. Nobody's going to pay you to research it. And I said, that's fine, Dr. Storms. I'm solvent. I'm solvent today. Okay. I hope you're ready, Dr. Storms, because you gave me some extremely valuable words. And I'll say it again. My time with you was a remembrance and a memento. This is my return favor. We're going to look at this electrode in the microscope, the shavings off the lathe. This electrode and this electrode were from the first fire. The reason I'm doing this right now is because I'm about to make a change, and I don't want a different result later that I can't document and go back to here again. So this video has some rhetorical value to myself. But I want you to notice something. These are pure carbon electrodes. They're copper cladded. Okay? These colors, when you smelt gold, those are the colors of gold and platinum and rhodium. Okay? So this is a visual spectrometry. This is Maxwell Planck, okay? Backed by the math of Marco Rodin. I've decided to include Marco Rodin in the board and the patent with royalties on the plasma force thruster. The reason I built this particular reactor. Because this is a true, proper fusion reactor. Fusion does not happen in a vacuum. It's a pressure. It's a gravitational pressure wave. Fusion is superconductivity. Fusion is gravity, and fusion is sound. Fusion is not electromagnetism, although you can use electromagnetism as a driving prime mover. And as you can see, my input versus my output. I put 500 watts in, all in, the hard way, or 100 watts in, the hard way. And I get 44,000 watts and 168 effective amps or 73 effective amps. Okay? That is a lot. I don't need a calorimeter. Okay? I do it in atmosphere for a reason, so I don't have to worry about the linear magneto effect optical effect of the bounce of any electromagnetism bouncing off some metal structure. I want to know what the temperature is up against ambient, because all cold fusion happened for 7/10 of a second and no more than 10 degrees over ambient, all in, as per Edmond Storms. So we're going to stay on that dictionary. The half-life of back EMF is 0.75 seconds. It all makes sense, okay? Edmond Storms had a crack theory. He is the only human being on the planet with the correct theory. But Edmond Storms knew that I was right. He now knows that I'm right. But he told me some very wise words. And those wise words were, you may be able to perform fusion, but you are not going to get a patent. I said, but I can explain how my circuit works to make it work. And he said, that may be enough. However, if I can explain why it works and quantify that, I can own your patent in the applied physics of a validated patent, where you have to show not only that it was you that made it happen. In my case, it's my circuits. So I have more protection than anybody in the world because my circuits are copyrighted and they've been on the internet very long, and my wave patterns and my oscilloscopes and my tutorial are copyright. I have never disclosed one patent on my circuits. Never. Now, I'm disclosing the second one. The first one is this thruster. The second one is fusion. This is a patent disclosure, and I have legally 1 year after today, which is January the 2nd, 2020, to file my patent. I can file my patent comfortably tomorrow. So Edmond Storm said, until you can explain why, I recommend you keep your mouth shut. Yes, sir. I have. You're going to see why your theory is correct in a moment. I'm going to set this here while I adjust the gain. This is a refractive light microscope. So the closer that I get, the denser. The further I get, the less dense. And then I gotta adjust the focus to deal with both of those. but this is for ferrite and laser machining in the micro millionths of an inch with extremely sensitive surfaces. Okay? Okay. I have one parameter set. Okay, I have the second parameter set. I have the third parameter set. Okay, I have quantification. Okay. This is carbon. About as pure as you can get. There's the grain structure. I want you to notice how tight the grain is. Okay? Now I have to put the phone down and the camera so I can move the microscope again. So this is on the body of the electrode. I'm not changing the focus. I'm just locating the table. Okay. Now as you can see, we're at the tip of the electrode. Do you notice the grain has expanded tremendously, almost in the ratio between graphene and carbon. The carbon is 900 nanometers squared. The graphene is 2,350 nanometers squared. Okay? Now I'm going to stay at the tip and I'm going to try to focus, but it's going to be almost impossible because of the depth. Do you see how blurry the rest is? I stayed at the same height and the rest of it is blurry because it's got depth. That's what a refractive light microscope shows you. A regular microscope will do the same thing, but a refractive light microscope has a special dial. It has a compound, 2 compound dials to get your density and your focus. So now I'm going to adjust to try to get just focus. I set density. I don't want to mess with density so that you can see I just focused in. Anywhere I go, there's expansion. So Edmond Storms was technically correct because he found that the metal was fractured from stress. So he concluded that must be the logical location of cold fusion. So he loaded electrodes. He knows about loading electrodes. I can load electrodes really fast. Okay, I don't care. because this is possibly a crux of an argument. I simply told Edmond storms it has nothing to do with the palladium. That's an imposed frequency based on Planck. I possibly did not say Planck. I probably just said that's an imposed frequency because I knew what the frequency was. And it didn't matter which metal that I used, I still got a lot of heat. Okay? Now, let's take this one step further again. And we're going to go a deeper quantification because this is for a very important person. Okay. My density, give me a moment. I am turning this dial. Okay. My density is pretty much spot on. This is this. I cherish my controls more than anything. These are the same four chips of metal that I've been showing you in the introduction of the Cooper-Puchta chains, where we have proven that we can take carbon and directly convert it to graphene inside of a metal lattice. So one moment. I'm going to go over that really quick because it plays importance. This is an atomically correct, fractal geometry correct, mathematically correct atomic structure of copper and carbon, where carbon is a ball. Once the superconductivity experiment happened, the empathy of the carbon brought all of the heat out and raised the energy level back to graphene, allowing the graphene to be a revolving door inside the ball lattice of the metal that they were using, because it didn't matter what metal they used, except almost all metals shall superconduct at a certain temperature, leaving you with the quantification and clarification that there's the carbon. The metal is immaterial what it is. Okay? So during the superconductivity experiments, they dealt with the simplified understanding of the Meissner effect, where they thought that the magnetism was going around the outside. That's not what was happening. The neutrons in superconductivity is where magnetism induces the field of electromagnetism. Neutrons are where gravity is induced from the proton. The proton is graphene, produced by 0+ vacuum, past absolute vacuum. We know this because we pulled 40 inches of mercury with water. Okay? The backward way. Now we know that there's another side to the periodic table that is hydrogen bound and vacuum related. We're just thinking to zero. There's the other side of the hourglass. And I have 4 metals that are hydrogen bound with no carbon. And I have atomic, correctly predicted physics, chemical chains on that subject. They just happen to be squared heterodyne Planck. So during the superconductivity experiment, the superconductivity froze the lattice, allowed the graphene to rotate and zip those electrons, proving quantum tunneling, validating Einstein's theory of relativity in this fashion. Graphene expands. Graphene can extremely expand. Graphene expanded and was induced until critical adsorption rate and cracked the metal. But graphene in space is the fabric of space that rolls our gravity from the neutrons. So, here's actually what's happening in superconductivity at the ground state. Here's what's happening when you try to test it with electromagnetism. Okay? Because it switches at 26.4 terahertz way before the electron can even get there. Basically, if you were to put it in year time, the electron got out the chauffeur door while the doormans waited 26.4 trillion years for you to get there. And then it goes, switches. Okay, come on, electron. I'll kick you through the door. And I'm going to amplify you because I'm tired of waiting for you. So we can get you to your speed limit to the next door. Because he's been waiting a long time. And back and forth. And they can squeeze through because the door can open. The door can open from this to this. This is a geometrically, fractal geometry, correct pattern of what you see of the bow tie of superconductivity on my oscilloscope, proving that I make the power to amplify superconductivity, amplify gravity, and amplify fusion. There's the tunnels. Right there. A quicker demonstration. Cooper pairs. Cooper Puchta chains, honorably. Carbon. Carbon balls. Electron. Carbon electrons, 2 in the center, 4 on the outside. These are magnetically put together and magnetically correct. Okay? So as the electron tries to go around the carbon, it splits. It wants to tunnel. It splits. Contracts and splits again. Trying to fight between the two yandras of that half second or 0.75 second versus the push back EMF of electromagnetism. So it's been there the whole time. But this is what's happening. The graphene goes flat in my energy. It doesn't expand. It does expand, but it allows the metal to do the phonon resonance with it and change the crystalline structure of the tunnel so that it can expand and still keep going because I continue to induce the field. Okay? So we have ground state. I cannot pick this one up, but if you notice, the electron is hanging out. On this one, the electron is, you see how it's bouncing? But I can pick this one up, and this is just a field. Okay, it's not two magnets repelling each other, it's just a field. Okay, so I flip this one over because the field is being induced through this metal to complete the circuit. It'll do it without the metal, but it's more dramatic with the metal. This one wants to tunnel. But see, now I can just pick up this one. Okay? So we're still back on the basic principles of magnetism. The first piece of metal that you're going to look at is the same metal. All four samples are 304 stainless steel. I chose 304 because it has a lot more chromium. Okay? Higher metals have more nickel, so you can get a better polish and luster. So this is the hot side of the chip when it was cut off the lathe. Now, there's two things you have to notice. Color and the difficulty I'm having with the light reflection from the camera. Okay? And then the third observation is, I'm going to give a little focus. You see how the cracks have smeared? Okay? That's basic tool hardening for machining. I didn't use any metal on any lubricant on any of the four pieces, and I just used a standard cobalt bit. I didn't sharpen it, I just grabbed it. Okay? Now we're going to go over to the cold side of the metal. So this is just the chip that's flipped over. Okay, so I get a little bit better light refraction because it's dark, but it's still golden and you can see the grain. It's to be expected because the metal has been drawn and annealed. That's perfectly fine. We're not going to change that process. I have an applied patent on that process, but it's not important. What's important is that we have a lot of wire that's already been drawn and annealed. See that? Nice straight grain. You've got a little bit of overlap, but for the most part, that's because it got hot right there. Okay? So, you see how the grain started to weave once it got hot again? Allowing an annealed piece of metal in a cooktop to take a little bit more heat. Okay? This is to be expected. There's the cold. Nice, tight, straight grain. I'm going to assume that Edmond storms saw some expansion similar to this in parts of his spectrometry. Now let's look at the cold side of the electrode. Same stainless steel. I'm at the same density and focus, but you notice I get a very bright, you see that light reflection? I can't even see it. Now I have to go out to focus. I'm coming up to focus. But you notice the color now? There. There we go. The iris of the camera doesn't like the intensity of the flash back. Oops, give me 1 second. Because I was on the wrong piece of metal. Okay, here we go. Now here's the cold side of the electrode. First you notice how bright it is. It's pure. There's no more chromium. I'll get the iris back. It's silver. There we go. Okay. I'm going to have to leave it right there. Pardon me, because I'm trying to do two things at once. You see how silvery white it is? It's so bright that I have to move the camera off of the metal. That's phonon resonance from the photons. Okay?